Hello everyone, I'm going to present DGCL, an efficient communication library for distributed GNN training. Nowadays, graph neural networks are widely used in many areas, including social network, physics systems, and medical molecules. Like many other neural networks, GNN have multiple layers to train. Here we focus on the full graph GNN training. At the beginning layer, each vertex in the graph has a feature, which is a vector to describe its properties. Let's take a look at the computation procedure of a specific vertex, the blue one. In each layer, it aggregates the feature of its neighbors and updates itself to produce a new feature for the next layer. So it follows an aggregate and update pattern in each layer. Like other neural networks, training GNN is very computational intensive, so it's better to train them on GPUs. The focus of this work is to train GNNs on multiple GPUs. In the distributed setting, we first partition a graph to several GPUs, and each GPU trained is subgraphed. However, during the partitioning, the endpoints of the same edges may be partitioned to different GPUs. Therefore, to guarantee the algorithm correctness, each GPU needs to fetch some vertices from other GPUs before the aggregation. So in the distributed setting, the computation pattern of one GNN layer is changed to communication, aggregation, and update. There are systems designed for full graph GNN training. DGCL and PYG are designed for GNN training on a single GPU. NeuroGraph and ROC focus on distributed training. However, this system integrate communication and computation in a system, so the communication layer is not general to use. What's more, this system uses naive communication strategies, which are inefficient due to the complex GPU topology. Therefore, we want to build an easy-to-use and efficient communication library for GNN training. So if a system can train a GNN on a single GPU, it can use our library to extend to multiple GPUs. Now let's see why the naive communication strategy is not efficient on GPUs. Peer-to-peer communication is the most straightforward strategy. In peer-to-peer communication, each GPU fetch required vertices from other GPUs directly. However, it has two problems because of the complex GPU topology, which are the unbalanced communication and bandwidth contention. Let us use the DGSGP server as an example to illustrate the problems. There are 8 GPUs on two CPU sockets in a server. Some GPUs are connecting with NVLink, while others are connecting with PCIe and QPI. Different connections between GPUs have different bandwidth. Therefore, in a peer-to-peer communication, fast link may need to wait for the slow links, which lead to unbalanced communication. What's more, different GPU connections may contend for the same link during the communication. For example, when GPU 1, 3, and 4 send data to GPU 5, they all need to go through the QPI links, which means they will contend for the QPI bandwidth. Motivated by the communication problems of peer-to-peer communication, we designed DGCL, a general and efficient communication library for GNN training. Now let me first introduce the system architecture of DGCL. In this figure, the dark green parts are the components of DGCL and the light green parts are outside DGCL. At the beginning, DGCL read the input graph and GNN model from users, and then it partitioned the graph and planned the communication. The DGCL master sent the subgraph and communication plan to DGCL client so that they can communicate with each other according to the plan. Finally, the GNN system can do the training as in a single GPU and use DGCL for the communication. Therefore, DGCL is general for different GNN systems. Now let's focus on the core problem, the communication planning. Let's first formulate the problem. The inputs of the problem are the graph partitioning scheme and the GPU topology. We want to design an algorithm to do the communication planning of each vertex while considering the communication balancing, contention, and forwarding. Finally, our objective is to minimize the end-to-end communication time.
Given the problem setting, now let's analyze the solution space, which is the communication strategy of each vertex. Let's use a simplified GPU topology as an example. Assume we have 4 GPU and 2 CPU sockets connecting with different links. Assume a vertex is partitioned to the first GPU and it has neighbor on other GPUs, which means we need to send this vertex from the first GPU to GPU 2, 3, and 4. So, what are the possible communication strategies? A most straightforward way is to send from GPU1 to others directly, as in the peer-to-peer communication. However, it will go through the QPI link to reach GPU 3 and 4, which may be too slow. Another solution only uses the NVLink, where we use the GPU 2 and 3 to forward the vertex to GPU 4. Or we can use a more complicated strategy, which we send the vertex to GPU 2 and 3 and use the GPU 3 to forward it to the GPU 4. As we can see, all the strategies of a vertex is a tree, and it's easy to prove that the optimal strategy of a vertex is always a tree. Given the solution space, we use a cost model to guide our algorithm. Assume we know the strategy of all vertices. In our cost model, we first partition the communication strategy into stages, and we assume the communication on the same stage are happen at the same time. So in each stage, we know the number of vertices going through each link and the speed of each link. We can easily calculate the communication time on this stage, which is the maximum of the vertex count over link speed for all the links. By aggregating the cost of stages, we can get the overall cost for the communication. So in each stage of the cost model, we only consider the slowest link, which encourage our algorithm to balance the communication on different links to minimize the stage cost. Also, all the communication on the same link are aggregated together at the same stage, so the contention is considered naturally in our cost model. Given the cost model, we design a shortest path spanning tree algorithm to determine the strategy for each vertex. The idea is that we incrementally process the vertex one by one. So the heuristic here is we try to minimize the aggregated cost when deciding the strategy of a vertex. So when we process a vertex, we know the strategy of previous vertices. Let's say the current vertex is partitioned to GPU1 and is requested by GPU2, 3, and 4. From the cost model, we know the incremental cost if we associate the vertex on a link. So at the beginning, we find the smallest incremental cost from GPU1 to GPU2, 3, and 4. Let's say GPU2 has the smallest incremental cost among the 3 GPUs. Then we send the vertex from GPU1 to GPU2, and then we use GPU1 and 2 to find the smallest incremental cost to GPU3 and 4. Let's say this time we pick GPU2 to GPU3. And similarly, we use the same way to reach the GPU4. And finally, we get a spanning tree, which is the communication strategy of the vertex. The intuition behind the algorithm is that each time we extend our spanning tree to the GPU with minimal incremental cost, and at each time it tries to utilize the fast link and avoid the straggler links.
We conducted experiments on 2 types of machines with without any links. We compare with three communication baseline: peer-to-peer, replication, and swap. Replication baseline replicate K-hole vertices on GPU to eliminate the communication. Swap baseline use the host memory as the shared memory for the communication. We include 4 datasets and 3 GNN models.
We first compare the end-to-end performance to train GNN on different datasets. In each group of the figure, we provide the performance of DGCL, swap, peer-to-peer, and replication baselines. In each bar, the bottom part is the computation time and the upper bar is the communication overhead. From the figure, we can see that DGCL has significantly shorter communication time than peer-to-peer and swap baseline. Average across all graphs and models, the communication time of peer-to-peer is up to 4.5 times of DGCL, where the swap is up to 60 times of DGCL. We also report the performance of DGCL on GPU topology without any links. In such case, the GPU connection have similar bandwidth, but DGCL still outperforms peer-to-peer communication since it considers the bandwidth contention during the communication. We also give a breakdown analysis of the communication time that DGCL spend on different links. The results show that DGCL can effectively balance the communication time spent on different links. So now let me give a brief conclusion. We start from a communication problem in GNN training and give an analysis of peer-to-peer communication. Then we propose a general communication library with cost model and planning algorithm. Finally, experimental results show that DGCL outperforms other baselines on different datasets, GNN model, and GPU topologies. So please feel free to ask any question.